Yeah, thank you very much for the very kind introduction, and thank you very much also for your hospitality here. So everything is great. Before I start, I want to show some non-mathematics. So during my stay in China, I started working with Chinese ink, and this is a tree on the island of Yangtze Lake. And I also made a painting of some Chinese flowers. But now let me start with the official lecture. So the idea for today is I will give a low-level introduction into the topic, and I will cover the cut-elimination theorem for predicate logic. So this might be boring for the experts, but I guess later I will also cover some material which might be new for some people. But for those who have never seen cut elimination, it might be interesting to see how it works. But before doing so, I start with some elements of the history. So where did logic start? We go back to the Greeks. So logic basically started with Aristotle, and he is famous for explaining some logical rules, for example, the syllogisms. So what is a standard example? All humans are mortal. Socrates is a human, so therefore Socrates is mortal. More famous person in history is also Euclid. He is famous for writing a book about geometry. And actually, incompleteness already shows up in the work of Euclid, namely that the fifth axiom which he has is not derivable from the other four. Well, Euclid did not prove this, but he tried hard to do so, but he was not successful. Moreover, we have Plato. And Plato had the idea that the real world consists of ideas, and the world which we see is just the shadow of the real world. And this gives a nice fit with the idea of many mathematicians about mathematical objects. Now, we go a bit further in history. We do a big jump, several centuries, and we come to Frege. And what was the idea of Frege? He wanted to base mathematics fully on logic. So he has written a book, Grundgesetze, and it turned out everything was fine. He sent the book to the printer, and then at the final end, he got a letter from Russell, and Russell pointed out that there is an inconsistency in his foundation of mathematics. So there was a Russell antinomy. Now, I will not explain too much about the Russell antinomy, but I will point to the standard example in set theory. So Cantor investigated set theory, and his first idea was to form sets out of given sets using comprehension. Now, what is the idea of comprehension? If we have a property phi of sets, then we can form a new set. Namely, we collect all sets X satisfying the property phi of X. And the comprehension axiom says that there exists a set Z. Z is precisely consisting of those sets X fulfilling property phi of X. Now, this is a naive way of doing set theory, because Russell says, well, for phi of X, he takes a formula, X is not an element of X. And then we get that the element Z defined by the set of all x, such that x is not an element of x, has a certain property, namely Z is an element of this set if and only if Z is not an element of the set. And this is clearly a contradiction. Now, the question is how to overcome this problem. Well, there are different ways to deal with this. One way was to say we have to change the logic. That would be the idea of Brouwer. And he introduced a new type of mathematics, the intuitionistic mathematics. I will not go too much into detail, but he basically said certain principles are no longer valid in mathematics. We are not allowed to use them. A typical example is tertium non datur. If we have an assertion A, we cannot assert that the disjunction of A or not A. So in general, this is not derivable. The other option is to restrict comprehension in a severe way. It goes, so Brouwer introduced what is called intuitionism. And later there was the idea of predicativism, and this was suggested by Poincaré. Or Hermann Weyl. And here the idea is, well, in the scheme of comprehension, one can use any formula phi, but the idea in predicativism is to form sets in stages. If you have built up sets, you can build a new set, but only referring to the sets which you already have constructed. Then Hilbert said, well, that is too much of a restriction for mathematics. I want to continue with Hilbert's Cantor's paradise. We want no restriction in mathematics. So Hilbert set up a program and he said, well, we want to, in some sense, safeguard mathematics. So, well, first of all, one has to figure out what to do with the comprehension scheme. So one has to replace comprehension by something weaker. And in set theory, one replaces comprehension by the axiom of separation in combination with replacement. This is weaker than full comprehension. And Hilbert wants to have a proof that one cannot derive a contradiction out of this new set of axioms. So the idea of Hilbert was first of all, formalize all of mathematics. And if one has been done so, then prove that the corresponding formalization is free of a contradiction. And for proof, you're only allowed to use methods which are beyond doubt. Now, we all know that this is not going to work in this full generality, because we have the results by Kurt Gödel. And Kurt Gödel said, well, he proved his famous, first he proved his completeness result, which everybody will know, but he is also famous for his incompleteness results. And incompleteness results, well, I will not explain them in full generality, but one formulation, it's a very specialized formulation, is that there are assertions phi in the language of arithmetic. Arithmetic is formalized using the piano axioms. So I write here the language of the piano axioms or the language of piano arithmetic. Let's say there is at least one phi such that phi is true in the model of the natural numbers. And moreover, the piano axioms, which are intended to formalize all the rules for natural numbers, is a set of axioms which does not prove phi. This is an example of an incompleteness result. Now, in our lecture, we want to find more concrete statements. So the example by Gödel is constructed by meta-mathematical construction. And we want to find an example which could show up in normal mathematics. And second, Gödel showed that PA, which formalizes basically arguing in finite mathematics, PA is not able to prove the consistency of itself, let alone the consistency of full mathematics. Therefore, these ideas of Hilbert were not working as expected. Now, this is not the end of the story, but somehow the beginning of the story. And it continued with Gensen. And Gensen was figuring out what exactly is needed to prove the consistency of PA. So what he proved is two things. First of all, he was writing up a scheme for transfinite induction about ordinals in PA. Now, ordinals are not members of the natural numbers, so one has to work via a sort of description of the ordinals with natural numbers. But anyway, he could show PA does prove, after a suitable formalization, that for all alpha less than a certain ordinal epsilon 0, the arithmetic is able to prove the transfinite induction up to alpha. And secondly, PA does not prove the transfinite induction where one replaces alpha by epsilon 0. I will explain later in my talk what epsilon 0 is. And the third one is PA plus the transfinite induction up to epsilon 0 proves the consistency of PA. Now, this is maybe not so surprising to prove the consistency of the induction for natural numbers by using the induction up to epsilon 0. But what is important here, that one can restrict oneself to quantifier-free formulas. Now, this scheme of transfinite induction up to epsilon 0 is the extra ingredient which we have to add to piano arithmetic to prove the consistency of PA. Okay, and then the proof series started, namely, what about theories which are stronger than PA? Well, in the last century, Weiermann and Schütte were able to characterize the strengths of predicative analysis. Predicative analysis formalizes the idea of predicativism in the style of Poincaré and Weil. And they characterize the predicative analysis using a certain ordinal, which is called gamma 0. But in my talk, I will not going too much into details about this. What is the state of the art nowadays? Well, ordinal analysis has been pushed further and further, and the leading experts in the area are Michael Rathjen and Toshiyasu Arai. And they were able to push the ordinal analysis to very strong theories. But don't worry, I will not go into this. So what they did is beyond the scope of what we are covering here. Now, there's a different approach to proof theory, going back to Kreisel. And Kreisel had a sort of pragmatic approach to proof theory. So he was posing the interesting question, assume that we have a proof, a formal statement P, in formal theory T. What more, theory T should be consistent, of course, should be a mathematical theory. What more than the truth of the assertion do we know when we have a proof in a given theory T? Can we get extra information about this? And this has to do with the idea of unwinding proofs. And nowadays, Ulrich Kohlenbach is the world leading expert in the part of proof theory called proof mining. And he has been very successful in applying proof theory to get to obtain concrete bounds for assertions which are proved, assertions about bounds which are proved by non-constructive means. Now coming to concrete incompleteness, I now switch to the board here, or maybe I continue here. Still enough space. There's still enough space here. The first breakthrough for concrete incompleteness was done by Paris and Harrington in 1977. And they showed that a slight modification of the usual finite Ramsey theorem is a true statement, which is not provable from the axioms of the natural numbers. And then shortly afterwards, Harvey Friedman was exploring more of these examples, and he came up with his analysis of Kruskall's theorem. He showed that Kruskall's theorem is not provable in predicative analysis, and that what he called miniaturization is a statement, a concrete statement, which is not provable in predicative analysis, therefore not provable in Peano arithmetic. And this finally leads us, these are examples of concrete incompleteness. This leads us finally to discuss phase transitions. So we have a certain number, C is what? It's a complicated number, 0.63. 95776, something like this. And then if one looks at the miniaturization of Friedman's theorem, one has, if R, rational number R is less than or equal to C, then PA does prove the Friedman miniaturization of Kruskall's theorem for function R times binary log. And if R is bigger than C, then PA does not prove Friedman's version of Kruskall's theorem for R times binary log. In our lecture, we will cover this result. And here we see a phase transition located by this number. So much for the introduction. Now, what is required to attend this lecture? I will only assume knowledge of predicate logic. we should have seen some sort of logical system, how to set up proofs and something like this. Now, this course will start with Gensen calculus. So Gensen is a very important figure in proof theory. He developed what is called natural deduction and his Gensen calculus, and he was also giving the first analysis of the Peano axioms. Now we will start over here. And we will study what is called sequent calculus. Now, there are different versions of sequent calculus. And every author has its own version. So we'll just choose one. But the presentation is basically independent of the choice of the sequent calculus. So whatever you take, when you have seen the result for one calculus, you will be able to translate it into another version. What I'm using here is a set of lecture notes by one of my former professors, Justus Diller. And he has used in his lecture notes a very compact notion of Gensen calculus. And we start with certain conventions. The conventions are not that important, but sometimes useful. And it starts with the following. Namely, the first convention is we have an countable infinite set of free variables. And we have the countable infinite set of bound variables. In most logic texts, there is no distinction between free and bound variables. But for proof theory, it's very useful to make this distinction in advance. Now, one assumes let a language for logic L be given. So what does this mean? We have fixed a set of constants, a fixed of function symbols, and a set of relation symbols. I will not write this on the board. If L is given, then one defines terms. Terms are defined as usual. So free variables are terms, constants are terms. And if a sequence of terms of length n, and if f is a function symbol of arity n, then f of t1 to tn is a term. It's important that in terms are only free variables, no bound variables. Of course, there's no quantifier in a term. Now, if you have terms, we define formulas. Now, formulas are looking as usual, right? So if you have terms, we have equality between terms. So we treat the equality as a relation symbol, which is logical, so not part of L. So in L contains the set of non-logical systems. And we assume that the equality is a logical relation symbol. We have equalities, and if you have a relation symbol P of arity n, and if you have a set of sequence of terms T1 to Tn, then we have this atomic formula P of T1 to Tn. Okay, that's nothing special. Now, we have also a special symbol for falsity. This is a formula which is false in every model. Stands for a contradiction. Now, we only have implication as connective, and we assume that we define the other connectives using implication. So if A and B are formulas, then A implies B is a formula. Okay, nothing special. And if we have a formula phi, if X is not bound in phi, not bound in phi of A, for free variable A, then for all X, phi of X is the formula. Yeah, this looks as usual, that's fine. Now, what is the trick? Why I'm doing so? Well, there's one important point, namely, if phi of A is a formula and T is a term, then phi of T is a formula. This is generally not true, because in normal logic you have to fulfill substitutability conditions for T. But if you have a distinction between free and bound variables, terms are always substitutable. So it's not that after the substitution of T, a variable of T can be bound by quantifier in phi. Now, okay, and then we define abbreviations. So negation of phi is what you would expect. It's a formula phi implies falsity. Now, it's a bit more tricky to deal with conjunction and disjunction. But you will be able to figure out, right? Define conjunction and disjunction using arrow and falsity. Now, how does this work? Well, for example, if we have pi and psi, it is what? It is negation of the implication from phi to not psi. And using a truth table, you can figure out that this is the same. And an extension formula is defined also by the roots of De Morgan. There exists x f is the same as not for all x not f. Okay, these are the formulas. Now we are speaking about the sequent calculus. So what is a sequent? A sequent is a pair gamma delta, where gamma and delta are finite sets of L formulas. What is the idea? The idea is a sequent formalizes, or intended semantics is, from the conjunction of gamma, I conclude the disjunction over all the elements in delta. And the Gensen calculus is setting up a logical system for sequence. And sequence can be turned into formulas by this type of interpretation. Now, what's the point with Gensen calculus? The point with Gensen calculus is that in some sense one can get rid of the most famous rule in logic, namely the modus ponens. If you have a Hilbert-style calculus, you can basically assume that modus ponens is one of the few rules for writing up derivations. And in Hilbert-style calculus, you cannot get rid of modus ponens, but in this context, you can do so. Now, before continuing, I clean the board on the right-hand side. So you may wonder why I'm so explicit, but the point is, if one wants to prove something about the calculus, you have to define the calculus. Otherwise, it will become problematic. So we have axioms in the calculus, logical axioms, two sorts. If you have gamma and the prime formula P, prime formulas are just the ones of the form equations or T1 to Tn. If you have a prime formula P showing up in what is called antecedent and succedent, this is an axiom, basically because P implies P. Moreover, another axiom is from falsity. We can basically derive everything and also in context. This is ex falso quodlibet, and from the false formula you can derive everything. Then we have logical roots, and the reason why I took this restricted form of formulas is that the gensen calculus will contain very few rules. So we have logical rules. Now we have rules for implication. So we have the rule for introduction of implication in the succedent. So if you have gamma, comma, phi, double dot, psi, delta, then if you have derived that one, we can derive from this premise the conclusion gamma, double dot, phi implies psi, comma, delta. Now this looks a bit difficult, but if you always look at the intended interpretation, these rules are correct rules. If you do a small verification, then you see that this is a correct rule. You have a corresponding rule for error introduction in the antecedent. That's a bit more complicated because it looks like a rule for the introduction of an end, of conjunction. And if you have a conjunction, you need two premises. Now, if you have gamma, phi, delta, and if you have gamma, psi, delta, if you have both premises, then we can derive gamma, comma, phi implies psi, double dot delta. Now we have rules for the quantifier. Very dangerous is the introduction of universal quantifier in the succedent. So if you have gamma, double dot phi of A, delta, and now A has to fulfill a variable condition. A is not in the three variables of gamma, delta, and for all x, phi of x. It's an eigenvariable condition. Then we can conclude gamma for all x, phi of x, delta. We have a corresponding rule for the universal introduction in the antecedent. So if you have gamma, phi of t, double dot delta, then we can derive gamma for all x, phi of x, double dot delta. Now, what is the intended semantics? If you have for all x phi of x, then of course you have phi of t. And if you can derive delta from phi of t, then you can derive the delta. Then you have rules for equality. There are three rules for equality. So we have the trivial equality t equal to t always holds, sort of axiom. Then we have a rule, so that's the rule for equality for identities. Then we have the rule equality for functions. So what can we do with f of s equal to f of t? Well, if you have this premise, then we can derive gamma s1 equal to t1, sn equal to tn, double dot delta. The argument is as follows. If the si are the same as the ti, then f of s is equal to f of t, and then we can obtain delta. If a corresponding rule for predicates, so the premise is gamma r of t delta, and the conclusion is gamma r of s. So these vectors stand for s1 to sn. And here we have a sequence of equalities. And that's the rule, the equality for predicates. Finally, we want to model modus ponens in our proof system, and that's the cut rule. How does the cut rule work? We have a formula phi, the cut formula. So we have two premises. Gamma phi implies delta, and from gamma we can derive the disjunction of phi and delta, and then we can conclude from gamma we can derive delta. And this formula here, phi, is the cut formula. Now, the theorem by Gensen basically says in a derivation of a sequent from an empty set of axioms, we can find a derivation where the cut rule has not been applied. Now, in the context of theories, we have an additional rule. So if T is a set of axioms, so if T is a set of closed formulas, then we have the T rule. How does the T rule work? Well, if you have gamma phi proves delta, phi is an axiom of T, then we can conclude the sequent gamma delta. This basically models that T is a set of axioms. Okay, these are the rules. Now, what are the proofs in the system? And I will be quite explicit in writing down what derivations are. So, proofs are defined inductively. We're setting up trees. So, derivations. If we have a logical axiom, if gamma delta is a logical axiom, then this axiom is also considered to be a proof tree. And we have a proof tree just with one root and labels consisting of gamma and delta. So then gamma delta is a derivation of height 0. Now we also want to consider derivations in a set of axioms T. So it's also a T derivation where T is a set of axioms. Now we have not used any axiom here, but any logical axioms is derivable in any theory. So that's the first one. So derivations are defined inductively. So I just give the inductive clauses. So if what? If we have trees, hi is a t derivation of a sequence gamma I delta I of height ni of hi, let's say, and if gamma 1 delta 1 gamma n delta n is a logical rule or a T rule, then the hi deriving the premises, then I form a new tree. The immediate subtrees are h1 to hn, and the new root gets labeled. It's a logical rule. Now I forgot what is the premise. What is the conclusion? So if this derives gamma delta, is a logical rule or a T rule, then we get the immediate subtrees proving these premises. Then we get a new subtree with conclusion gamma delta. Gamma delta is standing at the root. And what is the height? And this is a T derivation of height. Well, we take the heights hi at a new root. So it's 1 plus the maximum over h1 to hn. Now we say T allows the derivation of the sequence gamma delta if there is a T derivation of this sequence. And if T is an empty set of axioms, then I write just gamma delta is derivable, and the left-hand side is empty. Now, for preparing the cut elimination, I have to define a complexity measure of formulas. So the complexity of a prime formula, P, is 0. And if I have a composed formula, the complexity of an implication A implies B is what? Is 1 plus the complexity, the maximum complexity of A and B. And the complexity of a universal formula for all x phi of x is given by 1 plus the complexity of phi of A. So what is the idea here? A formula has a description by a certain tree, and the height of the tree is the rank of a formula. So we say this complexity measure is the rank of A. Now, with these definitions, we can come to the following very important definition. And we say gamma delta is derivable by a proof tree without axioms of height bounded by A. And index R means the rank of any cut formula in this proof is smaller than R. So this notion means there is a proof tree, there's a derivation of sequent gamma delta of height less than or equal to A, where all cut formulas have a rank smaller than R. So you see, it needs lots of time to develop the calculus, but once you have the definition, then you can start proving results. I will continue on the left-hand side. Maybe I wipe out these ones. We prove our first theorem about gensen calculus. Namely, if you have a sequent gamma delta, and in gamma and delta, we have occurrence of a free variable b. So we have gamma b double dot delta b. And we prove it with height bounded by a number n, and cut rings are bounded by R. Then we further assume variable b is only occurring at this position. So b does not show up in the free variables of gamma a union delta a. And b is also not the variable a. Then we can do what? We can substitute an arbitrary term for b. That's the theorem on substitution. So if you have derived a formula sequence with variable b, then whatever term t we have, we can plug in term t. Now here it's important that we have this distinction between free and bound variables. Every term t is substitutable in this context. Now the proof. The proof runs by induction on the height of proofs. And I will not give a discussion of any rule. But what's important here is last rule was the introduction of a universal quantifier in the succeedent. Because it is this rule here, and this causes problems. So assume that you have derived a universal formula from a premise what? So we have a shorter derivation of some ni r, and we have gamma b, and then we have delta b. And we have a formula on the right-hand side. Let's say for all x psi of x and b. No, this condition here only means that b shows up only at these places which are indicated and not somewhere deeper in gamma and delta. So I assume that I write gamma as gamma A and delta A, and then gamma B is, I take gamma A where I replace A by B. So I just want to stress that these are the occurrences of B which are shown. So the B is not hidden somewhere else. So everywhere where B shows up in gamma and delta, it is marked by this B. Now the term T is arbitrary. So for every term T, T can contain every free variable, in particular variable B, variable A, or whatsoever. Now, I prove this one by induction on the length or the height of the derivation. And now I assume what? Well, this is, you're right. It's not the premise, but assume that this is a conclusion, right? The last rule is derived from NIR gamma B double dot delta B, and here we have psi x, and let's say here's in variable A or whatever. A is a variable for the universal rule applied over here. Now, what's the point here is I can assume that this formula psi x, so assume that for all x, psi x, B is already an element in delta B. Then in the conclusion, it shows up on the right-hand side. Now we have the premise, gamma B, delta B, psi, not correct, psi A, B. And that's the premise for deriving this formula. Now, there are two cases. It could be that the formula already showing up in the premise, or it does not show up in the premise. Now, assume for simplicity that delta B is showing up in full over there. Then what's going to happen? Well, we want to apply induction hypothesis. So we replace B by T. And then we want to apply again our universal introduction in the succeeding. Now, this is not going to work. Now, here is a problem. The problem is that the variable A, for applying the universal introduction rule, the variable A is not allowed to show up in the conclusion. Now, if I have substituted term T it could be that term t contains a variable a. Then I'm lost. So that's not good. We forget about this. Now we have this here. And now comes the trick, important trick. So again, we use induction hypothesis, but instead of using induction hypothesis for B, we use the induction hypothesis for A. Well, sounds a bit funny, but in N1, this derivation is shorter than this one. So by induction hypothesis, we can substitute anything for A. And this is what we are doing. We replace A by a new variable. So we plug in here psi of C and D. C is not showing up in the three variables of gamma B, delta B, and for all x psi of xt. So we apply the induction hypothesis at a different position. So we replace the variable a by a new variable, which is called a fresh variable. You can do so. We have here still derivation height n1. Now apply induction hypothesis again. Then we obtain with the same height for the derivation, gamma b, delta b, psi c t. And now we have the situation that we can apply our introduction rule for the universal quantifier and the succedent, because the variable fulfills this condition. So we have chosen C in a way that is new for the context. For this purpose, it's also important to have enough space for choosing variables, but we have infinitely many free variables. So we are able to find the C. And now by universal introduction in the succedent, we obtain finally what we want to have. Namely, yes, B should be T. And here we have for all x psi of xt, but this formula is an element of delta of t. So here I assumed for all x psi of xb is in delta of b. If I plug in t here, it's in delta of t. Since we have here sets of formulas, this is the same set as delta t. And then we are finally, if achieved what we wanted to achieve. Now, if you want to train a bit more about this Gensen calculus, the other formula, the other thing we want to prove is weakening. So if you have derived sequent gamma delta, and if n is bounded by n prime, r is bounded by r prime, gamma is contained in gamma prime, delta is contained in delta prime, then we can derive with n prime, r prime, gamma prime, double dot delta prime. This looks also like a triviality, but it's not, because if we do the universal introduction, we have also to do the renaming of variables, because the delta prime can bring in new variables which are not in delta. And so we have to apply the same trick as here. And actually, we can sharpen this a bit by assuming that delta is contained in delta prime union positive. Then there is also some sort of inversion lemma involved, but you can prove it also by induction on n. Now it's a bit later than 11, but I suggest to stop here and to have a 5 minutes break. And then I will continue with the cut elimination theorem. So there's first an inversion theorem, and then comes the cut elimination. Okay, so now it's on my clock 4 minutes after 11. So I restart at 9 minutes after 11. Okay, so what did we see until now? We have seen the gensen calculus. I defined the calculus. I showed the substitution theorem, which works basically as you would expect. And there's also the weakening lemma that you can make your sequent bigger on the antecedent side and on the succedent side. And now I prove a theorem which is important for the cut elimination theorem, namely the inversion theorem. Now, what is behind the inversion theorem? Well, for the universal quantifier and the implication, we have rules for the antecedent and the succedent. And the idea is we build up a complex formula from formulas of lower complexity. Inversion basically says that in some sense, we can reverse certain applications of proof rules. So we have two statements. The first lemma is assume that we have a derivation of length n, bounded by n, and cut rings are all smaller than r. And I have an implication in the succedent. Then I can invert this. So the rule for introduction of an implication in the succedent has certain premises, and inversion says if you have the conclusion of an introduction of an implication in the succedent, then we can go back to the premises. Now, this is easy to prove. There's no special trick needed. We just do induction on n. Now, that's basically easy. Now, there's another one, which is slightly more complicated. Namely, the inversion of the universal quantifier. So the introduction of the universal quantifier would here require an eigenvariable a to conclude this one. But in the inversion, we invert to any term t. Now, the proof of assertion B is slightly more complicated than the proof of assertion A. Therefore, I will give a proof of assertion B. So if you want to train a bit in Gensen calculus, then you are supposed to prove A by yourself. Now, how can we prove assertion B? Well, induction on N. And then you have certain, you have to investigate what is this, what was the last applied rule. And there are all sorts of rules which can be applied, but basically the conclusion almost always follows easily from the induction hypothesis. There's one rule which is more complicated, namely when this formula for all x, phi of x has been introduced. So assume for all x, phi of x is conclusion of a universal introduction in the succeedant with premise. So the premise has a shorter derivation. And then here on the right-hand side, we have f of, what is this? Phi, of course. So we have here phi of A and delta. Now there's one problem, namely one has to be very careful in applying the rules, namely the formula which we have just proven could already have been there. So we assume that for all x, phi of x already shows up in the premise. We can assume this. So for avoiding case distinctions, we assume by weakening that this is always the case. That's the formula for all x, phi of x is part of the antecedent, as part of the premise. And if it is not case, and if it was not present in the premise, we just add it by the weakening lemma. But if it was part of the premise, and we do introduction over phi of A here, and of course we derive that formula. So this is a valid premise for the universal introduction. Now we have this premise here. Now we can apply substitution, the substitution theorem. So we get with NIR gamma, and now we replace phi of A by phi of T. Delta for all x, phi of x. Is this the formula we want to obtain? The answer is no. We want to obtain gamma phi of T delta. There's another formula phi of x here. Well, the point is, in this situation, we can apply the induction hypothesis to invert this formula for all x, phi of x to phi of T. Now, since the succeedant consists of sets of formulas, the double occurrence of phi of T is not harmful. We can just delete it because it's already covered by this occurrence of phi of T here. And then we can apply again weakening to obtain gamma phi of T delta by enlarging the height of the derivation. So that was basically easy. And the same proof applies for assertion A. Now this is not so difficult to show. What's now important? Important is so the heart of the matter is proving the cut elimination theorem. As I said, inversion is important for this. Now comes the crucial lemma for the cut elimination. It's the next theorem. And that's the key for cut elimination. It's a reduction lemma. How does this work? Well, we assume the following. Assume that we have derived the premises of a cut. So assume that we have derived gamma phi double dot delta with height bounded by n. And with height bounded by m, I have derived gamma double dot by delta. And assume that the rank of phi is less than or equal to r. Now, critical is if the rank of phi is equal to r. And if the rank of phi is equal to r, we cannot apply the cut rule, because cut rule in derivations of height of cut complexity bounded by r does not allow a cut of complexity r, only cuts with cut formulas of complexity smaller than r. So is it still possible to get gamma double dot delta? And the answer is yes. So we obtain. Now it's important somehow to get the sum of n and m. And for technical reason, we make our life easier. We have here 2 times n plus m are gamma delta. So in getting rid of cuts of complexity r, we cannot apply cuts, of course, but we have to find an argument how to eliminate cuts of complexity r by somehow cuts of smaller complexity. Now this has to be proved, and for doing the proof, I have to distinguish several cases, and now I need space, and well, I will somehow start on the right-hand side. So there are certain cases involved. And I will concentrate on the important cases. I will not cover every case, although not so much space on the board. So the first case is P is a prime formula. In this case, we use specific properties of our calculus. Namely, we have rules for equality introduction. We have rules for functions. We have rules for equalities between terms, composed terms, and for predicate symbols. And the rule is only affecting the left-hand sides of the calculus. And the trick is, if phi is a prime formula, then this phi is not the critical formula of one of these 3 rules: equality for the introduction of equalities, introduction of equality between terms, and equality or equivalence for relation symbols. So we do induction on M. And due to the formulation of the calculus, the induction will just go through. But this is somehow considered to be a routine argument, and therefore I will just skip it. The point is, this works nicely because due to the formulation of the calculus. Now, assume that phi is not a prime formula. Then there are again two cases. One is the formula phi is a critical formula of the last applied rule, and the other one, phi, is not the critical formula. If phi is not the critical formula, it's again easy. The claim follows directly from the induction hypothesis. I will also skip that case. Now, assume, therefore, phi is the principal formula. So, what could happen? Well, as I have to say that in this case too, the proof goes by induction on n. So if phi is not the principal formula, the induction goes easily through. If phi is a prime formula, the principal formula, then the proof is not so easy. So assume what? Phi is an implication. And it has been derived on the left-hand side. So what are the premises? We have one premise is the following form. Gamma double dot delta psi, and the other premise is the form N2 R gamma E double dot delta. Okay, and now it's a bit oversimplifying. The formula phi, of course, shows up over here. And the formula phi shows up over here. So these two formulas are the premises of derivation of this formula here when phi has this form. Now, what is here the point? The point is that these derivation heights are smaller than n. What does this mean? We can apply induction hypothesis. So here we obtain times n1 plus m. The formula phi is cut out, so we get gamma delta psi. And induction hypothesis to this premise yields 2 times n2 plus m is r. Phi is cut out. We get these two sequence. And that's fine. We have here gamma delta. But now we have a problem. The problem is here's the formula psi, and here's the formula chi. And these are elements which are disturbing. So what we want to do is we want to prove gamma double dot delta without he and c. Now we are stuck because there's no way to get rid of c and he. Now if we are stuck in the proof, we have to use what we know. And the point is, one of the premises was we do induction on n, but as a side information we have that we have derived also gamma double dot phi delta. Now the reason why I've used, why I've proved the inversion theorem is that, well, phi here is an implication. This means to this side I can apply my inversion theorem. And that's very important when you get stuck in your cut elimination proof. You have to check what the extra information you can use. So what we can use here is we can invert the formula phi and get gamma comma psi double dot he comma delta. Aha. Now this is very useful because we can now look at this information and we compare it with this information. We see psi is here showing up on the left-hand side, here on the right-hand side. Now this means we can cut out formula psi. Now what do we know about formula psi? The complexity, the rank of formula psi is smaller than the rank of formula phi, which is less than or equal to r. This means the rank of psi is strictly smaller than r. So if you have this here, call it star, and this here is also star, no, double star. So if you apply cut with star and double star, we obtain what? Well, 2 times n1 plus m plus 1 r, then gamma, comma, e, comma, double dot, e, comma, delta. Now we have here the second conclusion, call it plus. Now compare this sequence with this sequence. He is here occurring in the succedent, here in the antecedent. So by cut applied to star and plus, we obtain what? Well, we go over to the maximum of those numbers plus 1. So we get here an upper bound. And now n1 is smaller than n, and 2 is smaller than n. Now here's a factor 2. This means I can add 2 times 1 to reach number n. So with 2 times n plus m and r, I finally arrive at gamma double dot delta. So you see it fits nicely together. You get what you want to show. And why does this work? Because the roots for the implication are symmetric in succedent and antecedent, and you derive the principal formulas using formulas of lower complexity. And so somehow you can replace a cut of larger complexity by cuts of smaller complexities. This was the case that phi was an implication. And in this case, I used here this extra factor 2 times n. Now I consider finally the case where phi is a formula for all x psi. And this case is somehow the most difficult one. So I wipe out here the inversion. And let me recall the statement of the theorem. Statement of the theorem is the following. So we had a derivation of n and r, gamma, comma, p double dot delta. And get the derivation of m and r, gamma, double dot p delta. And what we wanted to show is, claim is with 2 times n plus m and r, we can prove gamma delta under the condition that the rank of phi is less than or equal to r. Okay. We assume phi has this form and phi has been introduced. So assume we have the following situation. We have the premise, shorter premise. So we do induction on this n. And phi has been introduced on the left-hand side. So this is universal introduction in the antecedent. So we have gamma, phi, psi of t, double dot delta. This is the premise of the universal introduction in the antecedent. It's important. You have to recognize the formula phi, which we are going to introduce, could also be part of the premise, because this is the feature of sequent calculus. You can always assume by weakening that the formula which you are going to prove is already part of the premise. Now we want to come to gamma double dot delta. What we do is first we apply the induction hypothesis. So we obtain with 2 times n1 plus r plus m and r gamma, and now this phi is cut out with this phi. So we get gamma, comma, psi of t, double dot delta. Now we have to get rid of psi of t, and there's no easy way of getting rid of psi of t. So why does this work? Well, if we get lost in the proof, we have to use the other information which we have. And it's now that, so we do induction on this n, do some steps. And at a crucial moment, we have to switch the sides, and we have to consider the derivation where phi is in the succedent. So by inversion, and now it comes, here's the formula for all x psi of x. Now here the phi is now psi, and we can invert to term t. So inversion on m r gamma double dot for all x psi of x delta gives what? It gives m r gamma double dot, and here comes psi of t comma delta. Now what we see here is psi of t is showing here in the antecedent, in the succedent, and now we can apply cut. The rank of psi of t is strictly smaller than the rank of phi, which is less than or equal to r. This means the rank of psi of t is strictly smaller than r. So by cut, we can cut out the formula psi of t. Now 2 times n1 plus m is smaller than 2 times n plus m. And we obtain gamma double dot delta. So this works smoothly under the assumption that we have the inversion lemma, and the inversion lemma needs the substitution theorem, so it's somehow a logical sequence which we have to apply. But this is basically what we need. Now we can get rid of inversion. We only need our reduction lemma. And using the reduction lemma, we are able to show the reduction theorem. So the next theorem is reduction theorem. If we have a derivation of height bounded by n and cut rank bounded strictly by r plus 1 of gamma delta, then by going to exponential of n, 3 to the n, and cut ring is lowered by 1, we obtain the same sequence. And this is again proved by induction on n. So what are the cases? We have the logical axioms, they don't cause any problem. We have the rules for the implication. And what we do is we apply induction hypothesis, apply the same rule, we are done. We have the rules for universal quantifier. We look back what has been the premise. We apply the induction hypothesis, and when we're doing the same, we apply the same rule, and we are done. So the critical case is this application of cut rule with cut formula phi with a rank of phi equal to r. That is the most dangerous situation. So let us consider the case. So we have a shorter derivation. of gamma phi double dot delta and a shorter derivation of n2 r plus 1 gamma double dot phi delta. So what can we do? We don't apply a cut right now. So this was the premise of the induction. We apply induction hypothesis. Now we have to be careful. So here we have 3 to the n1 r gamma phi double dot delta. This is induction hypothesis applied to this derivation. And we apply induction hypothesis to the other derivation. So 2 times induction hypothesis. Aha. Now, the idea would be to apply a cut, but this does not work. The rank of phi is equal to r. So a cut is forbidden. But for this purpose, we have our reduction lemma. The complexity of phi is equal to r. So we take this upper bound. So the reduction lemma implies what? With 3 to the n1 times 2 plus 3 to the n2. And r, I can derive gamma double dot delta. Now the exponential function has a property that is closed under addition. So 3 to the n1 times 2 plus 3 to the n2 is less than or equal to 3 to the n. Since n1 and n2 are strictly smaller than n. Okay, and therefore from this we obtain by replacing this bound by the upper bound, 3 to the n r gamma delta. Now we have the reduction theorem, and finally we have theorem by Gensen. Namely, if we have derivation of a sequent gamma double dot delta, then we get a proof of gamma delta, cut-free proof, where the n is replaced by an iterated exponential 3 to the 3 to the 3 to the n, and the height of the tower is given by number r. This is just iterated application. So lowering cut rank by 1 needs 1 exponential. Lowering cut rank from r to 0, we have to apply the exponential r many times. And then this is the famous result. Every proof of a sequent in sequent calculus can be transformed into a proof which is a cut-free proof. Now there are 2 applications. Well, it's already 12 o'clock. So in logic, there are 2 applications, 2 standard applications of cut elimination. One is the theorem by Heilbert. And the other one is interpolation. And for proving those assertions about logic, it's very useful to have this cut elimination theorem. Of course, well, you have to know what these theorems mean. But basically, you write down your assumption, and then you assume that you that your proofs are cut-free, and then you can basically analyze your proof. So cut-free derivations have the property that you have complete control about the complexities of the formulas which are showing up in your proof. So the cut rule itself is very dangerous because when you apply the cut, you never know what was the cut formula. And if a proof without cut, then you see all formulas which are going to prove all sequence, they are built up from below, so to say. All the formulas showing up in your proof somehow bounded in complexity. Now the theorem by Abron in the simplest version basically states if we have a proof of an existential formula, there is an x phi of x. Phi is quantifier free. Then there exists a finite list of terms, T1 to Tn, such that we can derive the disjunction, or let's say the sequent. So if you derive such a formula, this means we have the sequent empty set double dot this formula. And then there exists a finite list of terms, T1 to Tn, such that we can derive the sequent where in the succedent we have formulas Pt1 to Tn, and the antecedent is just empty. And the proof works like this. If you have a proof of this formula, then you move this proof into Gensen calculus. Then you do the cut elimination. Then you have a cut-free proof of an existential formula. And then you can basically trace back what has been used in this proof. And you can basically look back, and the terms you are needing for deriving the conclusion basically look up, they show up in the derivation itself. You can just collect them from your derivation. And that's basically the main application of Gensen's, is one of the main applications of Gensen style cut elimination. But since it's now getting 12 o'clock, I will not give the proof. Or I could do it tomorrow. I have 2 minutes, but in 2 minutes it's difficult to give proof of this, so to say. I can only basically explain how this is proved. So first of all, you have to rewrite your extension formula in the calculus, because we have only used the universal quantifier. For this, you have to rewrite the extension formula using the laws of De Morgan. And then you have to move. So this is an extension formula showing up in the succedent, which means there's a corresponding universal formula in the antecedent. And then you have to look what are the terms which have been used for the universal formula in the antecedent. And then you just collect them one by one. Because the derivation is cut-free, you are able to collect them. And that's basically all. And that's basically the proof which is behind this. And the same happens when you do interpolation. Someone can calculate your interpolation formula just analyzing a cut-free proof. And all proofs will break down when you have a proof where some cut formulas show up which are of uncontrolled complexity. Okay, that's basically enough for today, I guess. Yes, so tomorrow I will cover piano arithmetic. So I will cover the standard results of piano arithmetic, transfer induction in piano arithmetic, and also the provably total functions. And it could be that I need a bit more than 2 hours, but I don't know yet. So I have to see.